All right, so welcome back to chapter 11, and we are now in section 4. And the topic of this section is the idea of the cross product. So let's recap really quickly. The first couple sections were based around vector operations such as addition, scalar multiplication. When we got to section 3, we introduced a certain way of multiplying vectors, which we called the dot product. And now we're in section 4. I'm now producing another way of multiplying vectors. So again, the idea is you start with the goal and you build the math to reach the goal. So the cross product, the way I'm going to unpack this is I'm first just going to start with the how-to, just the recipe, and then I'll come back and try to sell you on what the cross product can do for you, okay? So let's start with a couple quick things. So notice that the vectors that we're going to be multiplying are vectors in space, right? So vector u, vector v. And the way that we define the cross product is, first let's make a note of the notation. So now you're seeing the x, meaning as opposed to the dot. So again, that just tells you a different type of multiplication is about to be done. And then, although although the cross product is slightly tedious, as you can see, there's a lot of multiplication and arithmetic going on here. I would, if you understand the idea of a determinant, and you would have had to have had some exposure to matrices and determinants. If you have not, just relax for just a second, don't worry. If you have had some type of exposure to matrices and you have had exposure to the determinant, see if you can make sense of how the cross product, how this definition of our cross product and how the definition of a determinant are related. That's your goal. That being said, I have no prior assumptions that you have had exposure to matrices. So let's go ahead and just perform a cross product. Again, I have not tried to sell you on why you would want to do this, or even the geometry of what it is that you're doing. But right now, let's just use our formula. Ready? So in this particular case, for example 1, we have vector u and vector v defined for us. And now I'm only going to perform the cross product of u cross product v. I'm going to give you the answers to b and c. You can perform those on your own. So using the definition above, which I'm going to just try to keep highlighted for just a second, you can label u sub 1, u sub 2, u sub 3. So u sub 1 would be 1, u sub 2 would be -2, u sub 3 would be, in this case, 1. And you can also label v sub 1, v sub 2, v sub 3. My apologies, I gotta be quick when I'm using the stylus. So label v sub 1, v sub 2, v sub 3. So v sub 1 is 3, v sub 2 is 1, and v sub 3 is -2. Now, once you have those labeled, at this stage, you are just following your recipe, right? Let's just put everything in the right spot. And what you have is the following. So now I'm going to go ahead and start to finish this up for you. So we end up with 4 minus 1 minus, now I have -2 minus 3 And I got 1 plus, that is a -2, so that should be +6, yeah. All right, let's finish it, and then we'll just talk about it for just a second. All right, and now let me just make sure I didn't do any silly mistakes. 6 and 1 is 7. I got -5, and this negative here is +5, and 4 minus 1 is 3. Okay, so now let's stop and reflect for just a second. So recall that when you a dot product, right? When you multiplied using the method of a dot product, the result was you took a vector times a vector, and the result was a scalar. Notice when you use a cross product, you're still multiplying a vector times a vector, but now the result is itself a vector. Okay, and now let me try to explain to you the geometry of what's happening here, and more or less the goal. So this won't take long at all. Can you just imagine, so we have two vectors, v and vector u, that are in a plane, right? Now, what if you wanted to create a vector that would be perpendicular to both vector u and vector v? In other words, let me just be silly for a second. In other words, what if you wanted a vector, right, to that's perpendicular to these other orthogonal to these other two vectors? It would literally come out of the screen and hit you in your forehead, right? That third vector, that vector that you're trying to create, can be done using this type of multiplication. That is the property of the cross product. So what I know, so in other words, without plotting this out, here's what I know. I know that this new vector is perpendicular to v and perpendicular to u, right? Let's go back to our x, y, z axis. If you were to take the cross product of x and y, now I won't use x and y if you don't mind. I will use I, j, k. So if you take I cross product j, you will get k. So does that make sense to you? That the vectors that are the cross products are always going to be perpendicular to the two vectors you started with. Okay? So it's a beautiful thing. So that's kind of the goal, right? And then we build the math to reach the goal. Now, before I give you some more properties of the cross product, let me go ahead and give you the answers to part B and part C. So V cross U, this is what you should get. And the cross product of V with itself. Okay, so on your own time, you can verify that you are getting the same results. Feel free to pause the video and try that now. Let's at least note something here, right? Think back in your math career. Normally, anytime you were to multiply, let's say 3 times 2, that would be equal to 2 times 3, right? The order of which you multiply them doesn't affect the result, right? It's the commutative property of multiplication. But notice that you multiply cross product v is not equal to v cross product u, but they are very similar, right? They're just opposites. So you can just see the signs are different. Okay, so let's talk a little bit about some of the properties. I've already highlighted the algebraic properties. I'm not going to discuss as much as I want to discuss the geometric properties. So you can go through the algebraic properties on your own time, but I've already pointed out some of the things that you see, that u cross v is equal to basically the opposite, right? Negative v cross u. So u cross v is equal to negative v cross u. Let's actually go to the geometric properties of the cross product, which are, in my opinion, much more interesting and much more useful. So let's actually think about the magnitude of a cross product and how and what that would mean for us. So the idea is, let's start. So you have a vector u and you have a vector, that's horribly drawn. You have a vector v, you have a vector u. Okay? And you decide to take the cross product of that vector. Now, you wouldn't think that this would hold, but because the cross product, right? If you take the cross product of u and v, the only thing that we've really studied so far is that this new vector will be a vector perpendicular to u and perpendicular to v. But what's interesting about that is the magnitude of that vector is equal to the parallelogram that's formed. Right? It's equal to the area of the parallelogram that's formed from vector v and vector u. It's fairly easy to, I don't think I need to go through that too much. I mean, for example, we've already seen that if you were to add v plus u, that's just equal to the diagonal of that parallelogram. And now you have a very quick way of finding the area of a parallelogram. Right? Areas of like the area of a parallelogram can be, it's not as simple as just length times width, right? It's you have to account for the fact that you have two the opposite sides are parallel, but and they're congruent, but you have this odd angle here, this this shape to this quadrilateral. So, but nevertheless, you have a very quick way of finding the area of a parallelogram. Okay. Now, it's also true that, so we've kind of scratched, or what we've already discussed 4. Notice that the magnitude of the cross product, if you're not thinking about areas of parallelograms, you can also find the magnitude of a cross product by just simply taking the magnitude of u multiplied that by the magnitude of v multiplied by sine of that angle between u and v. The other properties, the other geometric properties, we've already really discussed. For example, I've already said that the cross product u and v is orthogonal to both u and v. We've already discussed that. The only other geometric property which you've seen is if you take a cross product, right? For example, in example C here, if you take a cross product and you get the 0 vector, that's true, right? That's true if and only if u and v are scalar multiples of each other. Now, do you know what I mean when I say scalar multiples of each other? Can you translate? Are you at that stage right now where you translate that to mean that they're parallel vectors, right? Wouldn't you agree that vector v is parallel to itself? So now what you have another tool at your disposal. Don't let this slide by you. If you take a cross product and you get 0, you know that your vectors are parallel to each other, right? They are scalar multiples of each other. All right, so let's go ahead and just continue with our other cross products. So example 2, let's see what they ask of us. So it says find a unit vector, right? So we want a unit vector, meaning magnitude of 1. And they want this vector to be orthogonal to the following 2 vectors. So right now, let's play some word association. When you read find a vector orthogonal to 2 other vectors, immediately you should be thinking cross product. Okay? Find vectors, vector perpendicular to 2 other vectors, you should immediately be thinking cross product. All right, so let's go ahead and set up the cross product for u and v. Now the way I like to set it up looks like this. All right, and let's proceed. So without scrolling back and forth between continuously scrolling back to our definition here that we're using, I'm just going to go ahead and get started. So this is the way when I'm doing cross products, this is the way that I like to think about it. So I like to think about determinants of 2x2 matrices. And I showed you that on the previous page. But you are welcome, right? You are welcome to follow this recipe as well, because that's really what's happening. But again, I always go from here to here, then to here, and then I just take my determinants. Let's go ahead and finish this up. So this ends up being 0 minus 3i minus 0 minus 2j, and that's going to be plus 3, it's minus negative 8, I believe. Okay. So finally, here is our cross product. Negative 3i plus 2j, and that ends up being 8 and 3, so plus 11k. All right. So notice that you've done a lot of great work. You found the vector. This vector is orthogonal to u and v. The only thing that it is not a unit vector. So the last thing to do is, if you recall, you want to maintain the same direction, you just want to change its magnitude. And we do that by let me just write it really quickly. So this was the formula when you're trying to find a unit vector in the direction of v. Only now, instead of having v, what we're going to have is u cross v. So, all right. So let's make sure we understand. So I need the magnitude. So to do this, I'm going to need the magnitude of this new vector. And that's just going to be the square root of negative 3 squared plus 2 squared plus 11 squared. So that's equal to the square root of 134. Okay, so now we know what to do here. So now it's going to be actually, I think I have enough room here. So this is going to be 1 over the square root of 134 multiplied by our vector. Okay, so I'm not going to distribute this for you, but you get the gist. So that would fulfill all the requirements that we needed, which is it's going to have a length of 1, and it's orthogonal to the two vectors that we were given. Let me just take a second and mention where I see students go wrong. There's really one place, and do honestly, there's one place in this application where the majority of the mistakes are clustered. Of course, a student would have to understand that vector v can be written as 2i plus 3j plus 0k, but most students recognize that. That's not where the mistakes happen. Let me now go ahead and show you. The majority of the mistakes happen right here. So this minus symbol gets students a lot of the times. I'm going to go back to the very first page. So notice that right in our formula for the cross product, this first minus symbol is what gets students. They either forget that it's there and they add they end up with a plus symbol here and a plus symbol here, but something to this nature. But this one is where the majority of the mistakes happen. So I've just forewarned you, that way you don't make those mistakes. All right, so what else do we need to do? So let's take a look at example 3. And we're a little bit spoiled because I've already produced the the picture, right? The figure with everything plotted for you. So we're a little bit spoiled here, but let's read the question. It says, the vertices of a quadrilateral are listed below. All right, so we have the following 4 vertices, and if you connect the dots, you will form a quadrilateral. Now, what we would like to do is we have 2 things. We would like to show that the quadrilateral is indeed a parallelogram. That's task 1. Once we've done that, we would like to find its area. Okay, so remember, the cross product can find the area of a parallelogram. But first, we need to demonstrate that it is a parallelogram. So in case you have forgotten, so I've drawn a parallelogram here for you, and there's two properties that need to hold in order to make the statement that the quadrilateral is a parallelogram. So the 2 properties is the opposite sides have to be parallel, and they have to be congruent, meaning the same length. And that is what we need to show. So how are we going to do this? Well, the way I'm gonna view this is I'm gonna start, and it's somewhat arbitrary, but I'm gonna start from point A, and I'm gonna form a vector from A to B, and I'm gonna form a vector from A to D. That's my first job. So vector A to B and vector A to D. Now, wherever I decide to start, so I started at A, I want to choose the point directly opposite of A. So I'm now going to start from C. and I'm going to form two more vectors. I'm going to go from C to B, and I'm going to go from C to D. So let me do that now. So C to D and C to B. Okay, so let me just take my time with the first one, and that way you know how I'm going to continue from here. So if I want to form the vector A to B, as you recall, we can do that by just simply, getting it, putting it in component form, right? So it's going to look like this. I'm going to take my time with this first one, and then I'm just going to give you the answers to the next ones. So A to B, in component form, as you recall, that would be, the initial is A, the terminal is B, so it's going to be, it's basically terminal component minus initial component, right out of the first couple sections. So that's going to be 2 minus 5, and that's going to be 6 minus 2, and that's going to be 1 minus 0. All right, now I'm going to go ahead and write it in the IJK notation that the majority of you are used to. So that ends up being negative 3i plus 4j plus k. All right, so you would do the same thing for these other vectors, and I'm going to go ahead and do that now. All right. And as of right now, let's take a look at our 4 vectors. And we need to be able to make a point to show that these are parallel and congruent. Now let's start with, you could show that they're congruent by just simply taking the magnitude, right? If I take the magnitude of A to B and the magnitude of C to D, A to B, C, does it make sense to you that if you take the magnitudes of these two, yeah, so if you take the magnitude of these two vectors, they would be equal. It would also make sense that if you take the magnitude of these two vectors, they would be equal. So that right there would show that since the magnitudes are equal, that would tell me the opposite sides are congruent. Can you also spot for a second that, let's just look at these two vectors. Can you see how they're, the signs are opposite, right? Negative 3i, 4j, plus 4k, positive 3i, minus 4j, minus k. That tells me that they're parallel to each other. And if you're wondering why, how does that show you? Remember, right here, if you could take the cross product, you would get 0. But more importantly, recall that you have u cross v is equal to negative v cross u. And that equals 0 if and only if the vectors are scalar multiples of each other. Scalar multiples is another way of saying parallel to each other. So those opposite signs tell me that it's also parallel. All right, so I get to answer yes, it is a parallelogram. And that's meaningful because that means that I can take the cross product, if I take the magnitude of the cross product, that is going to equal the area of this parallelogram. But what am I taking? Let's make sure you understand. I have 4 vectors. What am I taking the cross product of? Well, you want to take the cross product of A to B and A to D. Right? The parallelogram is formed from these two vectors. It is true you could also take the cross product of C to D, C to B, but I hope it makes sense that the cross product we need to take is going to be the cross product of A to B and A to D. All right, here we go. So the magnitude, and we need the cross product of, we got A to B cross A to D. And I've already shown you how to do a cross product twice, so I'm going to just give you the answer in this particular case. So that ends up being the magnitude of 26i plus 18j plus 6k. All right, and once you take that magnitude, that's the square root of 1036, or roughly 32.19. And there's your area. Okay. So at this stage, I've given you some of the geometry of what a cross product, the geometric properties of the cross product. We've practiced the formula for the cross product. And the last thing that I want to give you is just an idea of where this would be useful. Okay, and I won't actually do a problem using torque. Okay, but I just want to make sure that you understand how this could be useful. So again, just full disclaimer, I'm not my background is applied mathematics, not physics. So that's my get out of jail free card in case I say something silly. But so let's start with just a working definition. Torque is the measure of how much. How do I want to say it? How much a force is acting on an object that causes it to rotate. Right. So what you have in this case is you have some type of wrench, and then this is a horrible screw, but anyway, you can see it's being applied to the screw. And of course, it's now your job to, you're going to apply force to this wrench, right? Okay, it makes sense. If I mean, you could apply you could apply all the force here, or here, or here, or here. There's 4 different forces here, but only 2 of the forces would actually turn the wrench. So let's state the obvious, right? You can apply as much force as you want on this screw, but if your force is in this direction, my sincere apologies, but you're never going to get that screw off, right? Same way here. If you were to apply all of it here, so that the that axis of rotation, right? The angle at which you apply the force matters. So in this case, force F sub 3 and F sub 4, both of these would cause the turning of this wrench. But I think you and I know that the best place to apply the force would be at F sub 3. That is where you will get the most torque, the most amount of turn. So what are the things that affect torque? Well, first off, the distance from the axis of rotation right? You and I, if you know anything, if you have any background in, you know, mechanics or if you ever worked in a shop, if you know what a you know breaker bar is, a braking bar, when you can't get a screw off, right? Or if you're like my grandfather who just put a really long pipe over the screw, but that is to create distance, right, from that axis of rotation. Right, so the distance is important for torque. The magnitude of the force is important. All right, so how much force you push or pull, right, is going to affect torque, how much it turns. And finally, there's one more property here, and that is the angle at which you apply the force. Right? That angle of the force. And of course, that's again to the axis of rotation. Makes sense? Will you and I agree that the angle that produces the most torque is going to be it's pi over 2, right? It's going to be that 90 degrees, I should say 90 degrees of you know, to the axis of rotation, because you can apply that force in different directions, right? But so the angle also affects how much turn. All right, that is again best that your math professor can do with these concepts in physics. Take it or leave it. The last thing that I want to show you, and you know, and we're almost done with this video. This is very quick. The idea of finding a volume, right? What's interesting is if you have three vectors, so you have three vectors in space, and when if you think about how the sides are formed, right, based on these angles, there's a concept of what we know as, what we call a triple scalar product, right? As triple scalar product. And we know that we know that a scalar, right, so it's just a quantity, right? It's not a vector itself. But the way this works is, of course, we have our three vectors in space end up forming a solid. You can see the solid that's formed. The solid is what we refer to as I've always struggled with this word, but it's a parallelism. Piped is how you pronounce it. I just can't say it very fast. But what if you want to know the volume of this solid? Now notice how the employment of a cross product and a dot product can help you find the volume of that solid. So that's the last thing that we're going to do, we're just going to do this quickly. So you're going to take a cross product. That's good, right? This is going to produce a vector, and then you're going to dot product that with u, and of course that's going to produce a single value, a scalar. So that's what's happening here. We'll move quickly. So you're given, it says find the volume of the parallelepiped. And you can't see it very well, but it's here. They give you vector u, vector v, vector w. We're just going to simply apply the formula. Now, what I've already done is I've already taken the liberty of finding the cross product. So now the only thing left to do is take the dot product of u, right? So the dot product of u with that cross product. So u dot v cross w is the last thing that we need to do. And that's fairly simple. If you when you use cross products or dot products, it's going to end up being 3 times 4 plus, that's going to be -5 times -6, and finally 1 times -6. So that produces a scalar, and that scalar is 36. So I don't know what units we're in, but it's the the volume of this solid is 36. All right, that's going to conclude 11.4. Let's go. I just produced this this tool one more time for you. I will see you in the next video.